There we go. So on the estimation of generalized linear models in the presence of multicollinearity, I think the title is the most complicated of this speech. So perhaps I should have chosen another title. That is always an issue among statisticians, but we're not given the most selling titles to our speeches, perhaps. But I would just start with some basic, for me at least, basic statistics, and discuss what statistics is all about and what statistical estimator is for. So I just start within statistics, what we usually want to do is to sample. We have a population, and we want to say something about that population. And the population could be, for example, all individuals in Sweden, or whatever it is that one is interested in. And by sampling some 1,000, 2,000, 5,000 Swedish people, we want to say something about all Swedes, or all people living in Sweden. So that is usually the purpose of statistics. And usually, we want to have some information about population parameters. And here are 3 Greek letters then, pi, mu, and sigma square, where pi is a population proportion. So it could be the proportion of Swedish people that would vote for a certain party. We have mu, that could be the mean income of the population then of all Swedish people, and sigma square is a variation around the mean. And these are then estimated using samples, and then we have samples estimators such as p, x bar, and s square, where p is an estimator of pi. So based on, let's say, 3,000 people living in Sweden, we can calculate p, which would be the proportion in the sample that would vote for a certain party. We could calculate x bar, which is the proportion or the average income, for example, in the sample, and s square, which is a variation around the income in the sample. So we have population parameters, which are known, and then we have some sample estimators as well. And by calculating these samples estimator, we want to say something about the whole population then. And these estimators have some properties, desirable properties at least in statistics. And the most common property in statistics then, and usually, at least in classic statistics, the most desirable property is unbiasedness. And if we have our estimator here, x bar, that is an unbiased estimator if x bar, the expected value of x bar is equal to mu. So what unbiasedness means in statistics is that we shouldn't constantly over or underestimate the true value. So if we want to calculate the average value of income in Sweden, and we have a sample or several samples, then our average x bar shouldn't always be above the true value, or it shouldn't always be below the true value. It will, of course, sometimes be above and sometimes below, but there shouldn't be any systematic pattern in this. And if there is no systematic pattern in this, then we have an unbiased estimator. That is usually the most important. But sometimes we don't have unbiased estimator. It's perhaps not always common, at least. So instead, we discuss consistency. And the estimator is weakly consistent if the probability that the absolute value of x bar minus mu is greater than a certain error term goes to 0 as n goes to infinity. This is a very technical definition of consistency. But it just means that if we have a sample of, let's say, 3,000 Swedish people want to calculate the average income, then we calculate the x bar, and that is our estimate of mu. But as we increase our sample size, x bar, if we ask perhaps 300,000 people, then x bar will be closer to mu. If we ask 3 million people, it will be even closer. And in the end, it converges to the correct value, which is mu. So if we ask all Swedish people, then calculate the average income, then x bar, our sample estimator, will be equal to mu. So it implies that the variance tends to 0 as the sample size n tends to infinity, or as we sample the whole population. Another property of an estimator is efficiency. And often we can have several estimators that are unbiased. And then the most efficient estimator is the estimator with the minimum possible variance. And for example, for the average value, we could estimate the midpoint of the data by the average value, the mean. But there is also other estimators, such as a median, that you can use to estimate the midpoint. And the most efficient estimator is the one with the lowest variance among unbiased estimators. Both the average value and the median value, they are unbiased under certain conditions, at least. But it is actually the average value that is the most efficient. And according to this criteria, it is the most desirable estimator then of the midpoint of the data. So these are three properties. There are also other properties that I will not discuss today. But we have unbiasedness, consistency, and efficiency. So we want to have an estimator that is usually unbiased, but we also want to have precision in our estimator. We want it to be close to the true value. And it is not always that we can have both an estimator with good precision and with no bias. So this is what is usually discussed as a bias-variance trade-off in statistics. And perhaps it's even more in machine learning nowadays where they discuss this trade-off. Because usually a biased estimator, one can introduce a little bit of bias and get more precision into your estimator. But the unbiased estimator will have a higher variance, but obviously an unbiased estimator will have a lower bias, because bias is 0. So this is a bias-variance trade-off. And in my research then I've been suggesting methods where I introduce a little bit of bias in order to decrease the variance and increase the precision of estimators. And this is an illustration of the bias-variance trade-off then. I'm not sure if I can use. Yeah, I can use it. Here we have low variance, low bias. This is what we want with an estimator. We want to have precision here, and I mean, most are in bullseye. They are very high precision and in the middle. Here, instead, we have a very low variance. I mean, they're all scattered together, but it's clearly biased, upward biased. Then finally, here we have high variance and low bias. Here it's no bias, but it's scattered around bullseye then. While here, this is a worst estimator, then it has a high bias and a high variance. That is, of course, not a very well-functioning estimator. I mean, usually this is a situation we want to have, but usually this is nothing that we can choose to have. Instead, usually one chooses between high variance and low bias, or high bias and low variance. Those are the two situations. And in classical statistics, unbiasedness has been the main property, the most desired property, actually. One has, in general, picked estimators with a low bias and a high variance instead of this one. But high bias and low variance are increasing in popularity, especially in big data and machine learning methods. And so far I've been mostly discussing univariate situation. We have one variable, for example, the income. We have mu, the population income in Sweden, for example, and we estimate that using X bar. That is one variable we estimate, and that is a univariate situation. But often in research, of course, we want to have multivariate analysis of data. And I think this is from first sentence of the Mardia book, Multivariate Analysis. So multivariate analysis deals with observations of more than one variable, where it is some inherent interdependency between the variable. So instead of just one variable, like the income, we could, for example, have energy usage, income, and the size of a house. And then you have three variables. Then you want to investigate, for example, the linear relationship or the correlation between these three variables. And of course, for example, between energy usage and income, one assumes there is a positive relationship. So that is the multivariate analysis of data, and of course, the most simple multivariate analysis of data is to estimate linear relationships and correlations between variables. But another one is the multiple linear regression model, as shown here, where we have y here is a dependent variable, is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, all the way to beta pxp plus epsilon, where that y is a dependent variable. So a dependent variable could, in my previous situation, be, for example, the energy usage. And then we have x1 here, and x2, x3, all the way up to xp, they are explanatory variables. So x1 could, for example, be the income, and x2 could, for example, be the size of a house. And then we have beta 0, beta 1, beta 2, beta 3, all the way up to beta p. And beta 1 then would measure the effect of income on energy usage, for example. And beta 2 would have the effect of the size of a house on energy usage. So then you can measure the effect of one variable on another variable. And this is just a classical multiple linear regression model. This is a general linear model. I will come to generalized linear models later. But this is a part of the family of generalized linear models, actually. Finally, we have epsilon here. It's an error term. That is where the noise comes from. We will never, for example, perfectly capture energy usage using this simplification, a linear model, for example. Perhaps in general, people with a higher income tends to use more energy, but it doesn't hold for everybody. People don't behave in this linear fashion usually. So therefore, we also have an error term, which is denoted epsilon in this case. So this is a multivariate regression model then, or multiple linear regression model. And of course here, we have the data. We have energy usage, we have, for example, income, we have the size of the house. What we want to estimate is these parameters, beta 0, beta 1, beta 2. These are then the population parameters. So to estimate these parameters, one usually use an estimator noted ordinary least square, OLS. And that minimizes the sum of square of the error term. And here we can discuss the loss function, which is the sum of epsilon raised to the power of 2, which is equal to the sum of y minus beta 0 minus beta 1 x1, all the way down to beta pxp raised to the power of 2. And this is the error that we're making in our model, and that is what we want to minimize. And this loss function is not so difficult to minimize. You just take the first derivative with respect to the parameter and set that first derivative equal to 0. So you can, for example, take the first derivative with respect to beta 1, and you solve it for beta 1. You set it equal to 0 and solve for beta 1. And if you do these calculations that I will not show you, one can find an estimator that is unbiased, consistent, and the most efficient estimator under some, of course, statistical assumptions. So this is the classical method then. And of course, this is an unbiased estimator. And when estimating in statistics, we always have many assumptions regarding our data. And I will not cover all those assumptions here. Could be up to 10 different assumptions. But one issue that is not in fact an assumption, but a problem here, that I've been focusing a lot of my research on is a multicollinearity issue. And multicollinearity is usually defined as a situation when some explanatory variables, such as x1, x2, and x3 are intercorrelated. So if we once again have the example where y is energy usage, x1 could be income, x2 is the size of the house, then usually people with a higher income lives in a higher house, a bigger house, and therefore they are correlated. And this leads to a multicollinearity issue, which was defined by Ragnar Frisch during the 30s. And to illustrate the multicollinearity issue, one can use Venn diagrams, where in the first one here, we have no multicollinearity, no collinearity at all, actually. Here we have Y, which could be energy usage. We can have X2, which is income. So this part, then, is a part of the energy usage that actually our variable income explains. This part here is the part of energy usage as the size of the house explains. But there's no correlation, there's no intersection between X2 and X3. So we have no collinearity. This is a good situation. It's easy to separate the effect from income and the size of the house in this situation. While here we have a low collinearity, so we have once again Y, X2 and X3. We have this part is once again the part that X2, for example, income explains. We have this part that X3 explains. But now we have a low collinearity. Parts of what the income explains is also explained by the size of the house. And then we move here, moderate collinearity, the shaded area becomes bigger, bigger, and even bigger here for very high collinearity. So in this situation, almost all of the variation in energy usage, Y, explained by income then, that is also explained by X3, which is the size of the house. And then it's extremely difficult to separate the effect from one and the other. And this is denoted as a multicollinearity problem. It is not an assumption, but it is still a problem. So causes of multicollinearity. Some examples here could be model specification. Sometimes we cause multicollinearity by our modeling. It could be, for example, if once again have energy usage and income, then as income increases, then usage also increases, but up to a certain point, and then it's not really such a big effect anymore. And to capture this decreasing effect for high incomes, one have X and X squared, so income and income squared. And income squared will naturally be collinear, because it's the same variable that you have just squared then. And constraints on the theoretical model being sampled, sometimes one needs to include then two collinear variables. Such as if you want to study energy usage, often one wants to include income and often one wants to include the size of the house. So we have to include them. And it could also be that independent variables share a common trend, often in time series. It could be, for example, that shares of oil price company, they are very much dependent on the price of oil price. So they will move together according to this lurking variable than oil price. And then they will be naturally collinear, and that will cause a multicollinearity problem. So these are just some examples of multicollinearity and when it can occur then. And consequence of multicollinearity. I mean, the first one is really not consequence. I mean, it's still unbiased, which is positive. So coefficient estimates will still remain unbiased. And actually, if you minimize the loss function I showed you before, those estimators will even be the most efficient one. So they will be the estimators with the lowest variance among all unbiased estimators. So in that case, the standard method that one applies is the optimal one if we consider unbiased estimators. However, in my research and since the 70s, in this situation, there has been different biased estimators proposed, where you can actually increase the precision substantially by introducing, hopefully, just a small amount of bias. And that is what is called ridge regression. That was introduced by Hall and Kenner during the 70s, in statistics as well, at least. I think it has been around in mathematics before that. But And they showed that one can decrease the variance substantially when you have multicollinearity issue by introducing a little bit of bias. So instead of having, if we go back, instead of having this situation, this is a cause of multicollinearity. We have no bias actually, but we have very high variance. Then you can move to this situation with a high bias, and hopefully not a high bias, but a higher bias at least, and a low variance. And to estimate the parameters using ridge regression techniques then, one minimize a different loss function then. We still have the same loss function, the sum of epsilon raised to the power 2. This is still what we want to minimize, the errors. We still want to have as low error as possible, but we introduce some bias by having k some beta raised to the power 2, which penalize high coefficient values, and by that shrinks them to 0. So if we increase beta values here, then the loss function here will increase. So if we put in very high values of beta, the loss function increases, and that will not be the minimum point then. So by introducing this term then, k sum beta square, one shrinks or push the coefficients in general towards 0. So that will lead to an underestimation of the true parameter. So you introduce in general some bias here. But by using this, by penalizing high values that are usually way off then, one increase the precision in our estimators. And of course, we have introduced a new complexity here, a new parameter we need to estimate, and that is a shrinkage parameter, which is denoted k. And we have, if k is equal to 0, if we look at the loss function here, k is equal to 0, we only have this part, so then we're back to OLS, the unbiased estimator. If k here is equal to infinity, loss function will be infinitely big, and all parameters will be equal to 0. So of course, it should be a value between 0 and infinity, preferably as close to 0 as possible to introduce as little bias as possible. So that is the idea of by ridge regression then. So for this estimation method, we introduce some bias into the model, but we decrease the variance substantially. And especially in the situation where we have a multicollinearity problem. If we don't have a multicollinearity problem, it is quite pointless to introduce this bias. Then it's better to stick with unbiased estimator. So, if I should just discuss my contribution in this area then. In my research, I've been focusing on generalizing these methods for different types of regression model when the dependent variable is not quantitative, or when it does not follow a normal distribution at least. Samples of such models are logit, probit, count data models, and gamma regression models. And now we're into generalized linear models. This is a complete family of regression models, and where y does not necessarily have to be quantitative. And logit, probit models, for example, those are when y in our previous regression model then is binary. So it could be employed, not employed, for example. We could have count data models, which is number of doctors' visits, for example. It is still quantitative, but we need other models here. And we could have gamma regression models as well, quantitative regression models. But it's not normally distributed. So these are 3 different other models that I've been working on. And I've been generalizing the methods that Hall and Kennard suggested during the 70s and introduce them for this type of models, even though logit models was also already done during the 80s, actually, by Schaefer. I don't know how to pronounce his name, actually. And my contribution in this area is also that I've been focusing on finding better methods of estimating the shrinkage parameter k. And of course, the purpose is to find a value that decreases variance substantially, but still do not introduce so much bias. And I've been suggesting many different ways and evaluating many different ways of estimating this parameter. And yeah, just some published papers, and that this was the first one I worked on which parameters in logistic regression, where I just suggested some new estimators of parameters. 2011 then I also introduced together with Gazi then a method for Poisson models. This one in statistics and operation research transaction is perhaps my most cited but my most simple paper. We just did a large scale simulation of different K values and checked which one was best. Together with Muniz, who was a master student in Florida International University. And then finally, this is my latest ridge type shrinkage estimator. This is for generalized linear models with an application to prostate cancer data, forthcoming in statistical papers. So this one is more discussion of how to generalize all the different methods into the family of generalized linear models that has previously been suggested. And then we applied it actually on a gamma regression model then, on a data set. So this is, and of course there's still a lot to do in this area. This is a very big area nowadays, because in the compute-intensive methods, the big data and machine learning methods, shrinkage estimators is commonly used, even though they don't always know it. That is what they actually use to estimate the parameters in their algorithm. But future research is to consider high-dimensional data when the number of parameters increases with the number of observations. One could discuss this in Q-rate models. One example of Q-rate models is a survival model then, where one studies survival of firms, for example. And then finally, almost unbiased estimator is what people consider now as well, where actually one wants to minimize the bias of these models and make them almost unbiased, at least, not completely unbiased. But there is corrections that one can make to still keep the variance low, but make them almost unbiased. But there is a lot of research going on right now in this area. And that's it.
So when I met with Kristofer this week in the corridor, I said, please, Kristofer, keep it as simple as possible. And he said, I will hold the most simple presentation I've ever held. So just imagine where you could have been today. So my final question for you is, if you got to choose between statistics and football Malmö FF, which one would you go for?
Simple, it's football, of course.
It's football. Congratulations.
Yeah, thank you.